in order to analyze it the most appropriate way, which really is with a two-way analysis of variance, where population is one treatment and season is a different treatment, and that'll be the more appropriate way of dealing with those data than the way I asked you to do it for the first assignment. So while you guys work on that, we're going to move on to the next type of technique that you might be confronted with. This is a really common set of techniques that you'll find, I think, really useful to you as you move forward in your life. Can you guys see my screen? Not yet. How about now? Okay, good. All right, let me get Zoom stuff off of that screen. So this next technique that we're going to look at is called regression. And people oftentimes use regression and correlation as synonyms, and they're slightly different. And while statisticians may draw fine distinctions between the two, the common public doesn't really make a distinction between them. But regression is actually a situation where we're interested in what the actual relationship is between one continuous variable and another one, and we're interested in putting slope values on that. So is there a relationship? How strong is that relationship, and what is the nature of that relationship? And it can be a linear relationship or it can be a nonlinear relationship. It doesn't really matter, but it's a very specific testing of, in the case of a line, you know, if you have a cluster of points, we're actually interested, if this is the equation for a line, y equals mx plus b, where m is the slope. In regression, we're actually interested in what the numerical value of that slope is. Correlation is somewhat different in that we're really only interested in whether or not these things covary. So does x covary with y? And we may not be concerned with what the actual value of that slope is. We just want to know if the two variables are correlated, and to what degree are they correlated. Oftentimes that involves estimating the slope and things like this, but it's a different type of question in a way. The fact of the matter is we use the same techniques for doing both of these, for answering both of these types of questions. But this is a distinction that hardcore statisticians will want to make. So generally, these correlations and regressions take the form of a y variable, which is the dependent variable. So I've used these terms before, but this is where it really becomes obvious. The dependent variable is y, and it's dependent because it's dependent upon the x variable, which is the independent variable. It's a variable that you can, in theory, set if you're a researcher. B is the slope that relates x to y, and then a is just where the line that you're estimating crosses the y-intercept. And so if we have a set of data that look like this, we would be interested in knowing what the slope is that relates relative humidity to the mass loss. I'll explain what this figure is about, but we would be interested in not only what the slope is, but also where the y-intercept is for whatever line it is that we fit through these data. So this is the form of it. When I was in high school, we learned it as y equals mx plus b, but b is what this book, Sokol and Rolf, uses. And it's because in most statistical textbooks, slope values are oftentimes beta values. And so they use the term b for the slope. But still, whatever is multiplied times the x variable is the slope value. So There are different kinds of regression, and so it's important that you make the distinction between them. We're going to assume that most regressions are model 1 regressions, mainly because the rest of the world assumes that model 1 regressions are what all regressions are. But if you start delving into it too deeply, you will find that most regressions are not model 1 regressions at all. They are actually model 2 regressions. And it's just, I think, mostly sloppiness on the part of people and laziness on the part of people that they analyze their data as model 1 regressions, even when that's not appropriate. So what is a model 1 regression? A model 1 regression is where the independent variable x is measured without error. And generally, we think of this as being x is under the control of the investigator, and the x values are fixed. So imagine that you are a chef. Have you guys ever whipped egg whites before? Anybody ever whipped egg whites? No. Okay. I occasionally make this stuff called flourless chocolate cake, and it's decadent. It's basically butter, chocolate, eggs, sugar, and a splash of rum. And it's all mixed together. There's no flour in it. It's all mixed together. You separate the eggs, you separate the yolks from the whites. You whip the whites into stiff peaks, and then you fold that into this chocolate, butter, and egg concoction, and it makes this super rich, super creamy cake. And one of the reasons that it's so rich and creamy is that it doesn't have any flour in it. It's just really eggs, butter, sugar, chocolate, and a splash of rum. So one of the things that you could do if you were a chef and you were interested in the quality of egg whites in the whipping process is you could vary the speed that you have your mixer operating on, and you could look and see how long it takes to whip eggs into stiff peaks given different speeds of your mixer. So in this case, you, the researcher, are controlling the x variable, which is the speed of your mixer. You would set those values at whatever you set those values at, and then your response variable would be the time that it takes to get those egg whites whipped into a suitable degree of firmness. And so that would be an example of a type of regression where you, the investigator, have control of what the x variable is, you fix those things, and then you're basically looking for how does the y variable respond to those fixed x variables. So for any given value of x, y's are independently and normally distributed. This is one of the assumptions. And the samples along the regression line have equal variances. And we have ways of testing. So this is just the standard kinds of assumptions you make for parametric statistical tests. The residuals are normally distributed, and the variation of the points around the line is all similar across the width of the y of the x variables. So this is just the normality assumption and the homogeneity of variances assumption. There is a second type of regression, though, and in model 2 regression, both the x variable and the y variable are random variables. You, the researcher, don't have any control over the independent variable any more than you have control over the dependent variable. And the fact of the matter is this is how most regressions are. And generally what you have to do with this is you have to do what's called standard major axis regression, because you actually don't know which is causing which. In the case of the mixer, as you increase the speed of your mixer, you're expecting the time necessary to whip that to get stiff peaks is going to decrease. And so you know that there's this functional relationship between mixer speed and the time that it takes to get stiff peaks out of your egg whites. And so that's a functional relationship. X is basically causing Y. In type 2 regression, X may be causing Y, but just as easily, Y might be driving X. And you don't know which of those things are. So you've heard the expression, correlation does not mean causation. That's true. The reason that that expression is not regression doesn't imply causation is that regression generally does imply causation. Regression generally implies that as you, the researcher, vary X, Y responds. And that's what model 1 regression is. As you, the researcher, vary X, Y responds in a particular way. Model 2 regression says X might be causing Y to respond in a certain way, but it also says Y could be causing X to respond in a certain way. And you, the researcher, do not necessarily know which of those two things is actually the case. But people hardly ever analyze their data in this way. And once again, I think it's mainly because it's more difficult to do and people default to the easy thing rather than the appropriate thing. What you would generally do in this case is you would do a regression where X is the X variable and Y is the Y variable. And then you would do the regression again where Y is the X variable and X is the Y variable. And you would take an average of those two regressions. And it's sometimes called standard major axis regression. It's sometimes called geometric mean regression. But it's more of a pain in the butt to do, which is, I think, the main reason that people don't do it. So the example that we're going to work through in class is a really simple data set. It's looking at confused flower beetles. These are flower beetles that get in your flower in your cabinet. And it's looking at water loss under different conditions of relative humidity. And in this case, presumably the relative humidity was actually set by the investigator, although I'll explain here in a little while why I think that maybe that's not true. They weighed the beetles in 9 groups of 25 beetles each. 6 days later, they weighed the beetles again to register weight loss. The independent variable in this case is the relative humidity that once again was presumably set by the investigator, and the dependent variable is weight loss. So these are what the data look like. And in low relative humidity, it makes sense that in low relative humidity, that beetles would lose the most water because they're in a dry environment. And in a wet environment, you would assume that they would lose less water. And so that's the reason for this negative relationship. The higher the relative humidity, the lower the water loss of the beetles. These are what the data look like. So as I was looking at these data, it's like, well, this is weird. Why would the researcher have produced 1, 2, 3, 4, 5, 6, 7, 8, 9 different relative humidities, and one of them is 29.5, one of them is 53, one of them is 75.5. If I was the researcher and I was setting these, I would have probably set them at 0% relative humidity, 20% relative humidity, 40% relative humidity, 60, 80, 100, et cetera, et cetera. So when I look at these data, it seems to me that maybe this is not a model 1 regression, although the book that I took this out of basically says that the researcher did set the relative humidity. I don't know if they had equipment difficulties or what the deal was, but these relative humidity measures just seem to me to be odd. Why would you experimentally set relative humidity at 62.5%? Whatever. But this is the relationship. At the lowest humidity, the beetles lost the most weight. At the highest humidity, beetles lost the least amount of weight, and it appears that there's a nice linear relationship between these two variables. So the first thing that you'll want to do when you're doing a regression is you will want to get the mean of the X values and the mean of the Y values. So if you sum all of these up and divide by 9, you will get the mean of 50.389. And so we can do the same thing for the Y values, and we will get a mean of 6.022. And so we can go back to the figure here, and we can basically graph this on the figure. 50.389 is right here. The dotted line is the value, the mean value of the X variable. And 6.022 is the average value of the Y variable. So average relative humidity was a little over 50%, and the average weight loss was a little over 6 milligrams of mass. Now, if you're interested in how relative humidity affects mass loss, you might be interested in what the average mass loss is. But whenever we calculate an average of a response variable, one of the things that we pay attention to is how big the residuals are around this estimate of mass loss. And we can actually calculate those in the Y space by basically saying, how far is this data point from the average mass loss? How far is this data point from the average mass loss? How far is this data point from average mass loss, et cetera, et cetera, et cetera. And what you see in this pattern of regressions, well, what do you see in this pattern of residuals? You have a bunch of residuals there. What strikes you about the residuals?
It's almost as though they're mirrored.
Yeah, and so the first thing that you should notice is that the further away you get away from the mean of X, the bigger the residuals get. And on one side, they get bigger and bigger in a positive way, and on the other side, they get bigger in a negative way. And so there's this pattern to the residuals, but the pattern to the residuals is because this line set at 6.022, the line that is a horizontal line at the average Y value, that is basically a line with a slope of 0. And so if you have a slope of 0, and that's actually the null hypothesis. The null hypothesis in a regression is that you have a slope of 0. The null hypothesis is that the slope of this relationship is a slope of 0. The alternative hypothesis is that the slope is something different from 0. It's either positive or it's negative. Now, in this case, the slope would be negative because it's not positive. As relative humidity goes up, mass loss doesn't go up. As relative humidity goes up, mass loss goes down. And because the slope of the relationship is actually a negative slope, you get large negative residuals over here and large positive residuals over here, because a slope of 0 is not a very good fit to the data. A slope of 0 does not explain the variation between relative humidity and mass loss. And so what regression is going to attempt to do is it's going to attempt to find the equation of the line that goes through these data that minimizes the residual value. Let me repeat that. What regression is going to do is it's going to find a slope. It's going to find an equation for a line that passes through these data points such that the residual value, the residual distance between the line itself and the individual data points is minimized. And that's actually the test for, or that's the goal is to reduce residual variation around the line. And so how do we go about doing this? Well, we're going to be fitting a line that looks like this. This ends up being the fitted line. And if you look at this fitted line, you see that this residual here that was really big is now really small because you've got a best fit line going through here. This residual is now going to be really small. This residual is going to be smaller than it was before. This residual is going to be larger than it was before relative to the horizontal line. But overall, the residual variation is going to be lower. And I have a figure for this. Let me go forward a little bit. This is what the residual variation looks like with the best fit line. You can see that now all of these individual points are very close to the fitted line as opposed to these points that are very far from the line with a slope of 0. So how do we go about doing this? Well, in order to calculate the equation for the line, we have to be able to estimate the y-intercept, and we have to be able to estimate the slope value. To estimate the slope, we need the sum of the xy values, and we need the sum of the x values squared. And in this case, the x and y are slightly different, so I go through that on the next slide. So in this case, what we have is x is the deviation from the mean of x. And so in this case, x in this formulation is essentially how far is this value from the mean of x? How far is this value from the mean of x? How far is this value from the mean of x? And so if we think about this from a variance standpoint, remember that the variance is the sum of the squared deviations of each individual value from the mean squared divided by n minus 1. This deviation of each value from the mean of x, this is what this particular formulation is referring to as y. Because we have both an x variable and a y variable, we have to know what the deviation from the average of x is, and we need to know what the deviation from the average of y is as well. So if you're doing this in a spreadsheet, we can actually go and do this. Let me go and find the spreadsheet. So this data set is on the Moodle site, so you can download this data set and open it up. And here we have it. I'm going to make this bigger so that you can see it a little easier. So in all these cases, we can basically just use some standard formulas in Excel to get the average of relative humidity, and we can get the average of weight loss. And so this x value, which is the deviation of the individual values from the mean, this is simply going to be equal to that value minus the mean of that column. And once again, we can make these static cell references. Whoa. Static cell references. And we can calculate that for all of those data points. Now, what's going to happen when we sum these up? We can do it here in a minute, but what do you think is going to happen when you sum these up? Hannah, are you talking?
Is it going to be 0?
Yeah, they're going to sum to 0 because this is what all residual values do. Residuals always sum to 0. We can calculate the deviation of the y values from the mean, in which case we can actually just copy this value over to here. But in this case, we need to make this reference column B rather than column A, and it will give us all of the residual values for the y variable. And your prediction should also be that when we sum this up, that will also sum to 0, because this is the nature of residuals. So in this figure here, what we've done here is we have basically taken all of these values and summed them up, and we've taken all of these values and summed them up, and this should look just like this. So that's what that x and the y is. But of course, the whole reason that we square deviations typically is to get rid of the negatives so that this thing won't sum to 0. So we can basically take this deviation and square it. And that's what this next column is. We're going to take the deviations of each value from the mean of x and square them. This is very much like calculating a variance. Well, it's exactly like calculating a variance estimate, except that we're calculating the numerator of the variance. So we can take each of these values, so minus 50.3, we can take that and we can square it. And when we do that, this thing will now sum to some positive value. Okay? We can do the same thing where we look at the deviation of y and square it. Where we're basically going to take the deviation of y and square it and copy that down. And that will sum to some positive value also. And then the equations call for not only these things, but it also calls for the sum of the x values times the y values. And in this case, the x and y values that you are doing are these little x values and these little y values. So 50.389 negative times 2.958 negative. And when you do that, you should get these 3 columns of data, or these 2 columns of data. You'll have an x squared value and then an x times y value. So let's go back to our spreadsheet and let's calculate that. So this is x times y in terms of, this is it's the deviation of x times the deviation of y. And so if we take deviation of x, multiply it times the deviation from y, should give us 149, and that should be negative. And then those are all those values, and we add those all up. So the first thing we need in order to calculate this line is we need the sum of the deviation of x times the deviation of y divided by the sum of the deviations from x squared. That's what this equation says. So we have those 2 values now in our spreadsheet. The numerator is right here. So we can come down here and we can calculate slope. And slope is going to be equal to the numerator of that equation divided by the denominator of that equation, which is the sum of this column, which is the deviations from x squared. And we find that the slope of the line here is negative 0.053333, no, 0.32222 ad infinitum. Okay, so that's how you calculate the slope value. That's easy enough to do. So once again, it's not a super complicated sort of equation. We just find the sum of the deviations of x times the deviations of y, and then the sum of the deviations from x squared. Now, what we need to find is we need to find the y-intercept. Well, because the slope of the line is y equals a plus bx, we can solve for a by basically subtracting bx from both sides. Y minus bx equals a. And we can apply this using x and y as the averages. So we just take the average of y and the average of x, plug it into this equation with the current slope, and that will give us what the y-intercept is. So go back to your Excel file. We can basically say the y-intercept is equal to the average y value minus the slope times the average of the x variable. And we can see that the y-intercept is 8.704. When we go back to this figure here, we can see that the y-intercept of the best fit line is up here really close to 9. So up here in the 8.7 sort of realm. And when we look at our already prepared spreadsheet that is looking at all of this, is we find that the slope is negative 0.5322 and the y-intercept is 0.8704, which is exactly what we calculated when we did the calculations ourselves. So now at this point, we know that the equation for the line for this relationship relative, sorry, not relative humidity, weight loss equals 8.704 minus 0.053222 times relative humidity. This is the equation of the line. You've just calculated your first best fit line through a cloud of data. And all you really needed was a couple of columns of data. You basically needed these two columns of data, and you needed these two means in order to do that. Any questions about that? Haley, your roommate must have woken up.
Yeah, she did wake up, so the lights are on now.
Okay, good. So this gets you the line, but there are other things that we might want to know about the line. So we need to ultimately test to see whether this line has a slope significantly different from a slope of 0. So going back, what we really want to know is this new line that we just calculated, is this a better fit to the data than a slope of 0 line? And So what we're interested in knowing is the following. So what we really want to know is how much of this overall variation in y is actually accounted for by variation in x. So go back a minute with me to this situation where the assumption is that x doesn't explain anything about y. Knowing something about relative humidity doesn't tell us anything about mass loss. That statement is basically what you're saying when you have a slope of 0, when you have this horizontal line. So around this horizontal line is a bunch of variation. There's this much variation, there's this much variation, this much variation, this much, this much, this much, this much, this much, this much. There's a total amount of variation in y. Now, under the assumption that x doesn't tell you anything about variation in y, relative humidity doesn't tell you anything about mass loss in these beetles, this is the total amount of variation. But because we know that this is not the best fit line, we're interested in knowing how much variation is there around this the line here when it's a best fit line, whereas compared to how much variation there is around the line of 0 slope. So how does this line reduce total amount of residual variation? Another way of thinking about this is the regression line that you calculate is the average expected value of mass loss given some relative humidity. So as relative humidity changes, you might expect the mass loss to change. Well, what is the expected value of mass loss given some relative humidity? These are estimates that you observe, but there's an average value in the same way that when you have a treatment, there's an average value with some variation around it. Well, think of this as just the running average of mass loss as relative humidity changes. And so what we're going to want to do is we're going to want to calculate some other things. And so these other things that we're going to want to calculate is we want to calculate, for example, what is the expected value of mass loss at 0% relative humidity. So the way we can calculate that is basically the first thing that we have to do is we calculate what y hat is. Y hat, whenever you see a hat over something like this is the expected value or the predicted value, depending on what book you're looking in. Well, you get this by just plugging the x value into the equation. And so we would take this equation, weight loss equals 8.704 minus 0.053222 times x. And whatever that value is, that's the value on the line. So if we do that for each of these things, let's go and do it in Excel. Since we're doing things in Excel, we can do y hat. This is simply the slope value. And once again, we'll make this a static cell reference so that it applies this equally across everything. Plus, sorry, not the slope value, the y-intercept. The y-intercept value plus the slope value, once again, make that a static cell reference, multiplied times whatever the x value is. And so we should intercepts plus slope times relative humidity. Yep. So that should give us 8.704. That should actually just give us the y-intercept. And then these are the values for the rest of these things. So these are the predicted values. And what you should be able to find is that when you do this, these should be the points on the line. So if we go back to this situation here, at 0, this should be 8.7. At 12, it should be 8.06. So if we go back here, figure 12 is about right here. It will intersect the line at a little bit above 8, et cetera, et cetera. So these are just the points that are right along the line. It's basically saying for each of the X values that we actually identified, what is the point on the line at that X value? Then we might want to know, well, how far does the individual value differ from the predicted value? This is essentially calculating the residual of each of the points from the new predicted line that we've drawn. So before, we had a bunch of residuals that looked like this. And this is just the distance of the individual value from the mean of all of the y values. Then we calculated a new line. Well, now we want to know what's the distance between this value and the new line. What is this new residual value? And so what we can do to find that out is we basically just take we find the fitted line, and then we essentially take the y value minus the predicted value. And once again, because these are all residuals, what should this add up to? Yes, it should add up to 0. Thanks, Hayden. So we can always check ourselves and say, does that add up to 0? Well, it adds up to 5.77 times 10 to the minus 15th, which is really, really close to 0. And so that's probably just rounding error somewhere along the way. But this is basically, if we give this, let's format this cell and give it 16 decimal places. That's what that value is. It's for all intents and purposes, it's a value of 0. So this is the sum of the residuals. Well, then once again, because this thing essentially sums to 0, we need to get the square of that. The new residual squared, we basically just take this value and square it, and we copy those all down, and then when we're done with that, we can sum those values. So we can think about this as the sums of squares of y under a slope of 0, or the sums of squares of y using the best fit line. And in this case, the sums of squares of y under a slope of 0 is equal to the deviations of y squared. It's this value right here, 24.13. But the sums of squares under the best fit line is this value right here. So the residual variation around the line is way, 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 way smaller when you use the best fit line than it is when you use a line of a slope of 0. And so that's the whole purpose of generating this new line. Let me make sure that all of my numbers are the same. Yeah, 0.616. And so this amount of variation is much larger than this amount of variation because the line that we're fitting has reduced the amount of residual variation across this whole range of x variables. So this ends up being the sum squares residual. So in the end, when we test a regression, we're going to test a regression using the same kinds of methods that we use for ANOVA. There's a particular source of variation. There's a certain number of degrees of freedom associated with that source of variation. There's a sum of squares associated with that variation. And then there is a mean squared, and then we can calculate an F statistic. And so in this way, regression is just like ANOVA in some ways, except that the sources are somewhat different. In one case, the source of variation is due to the regression itself. The regression line itself explains variation in the data. Then there is variation that is unexplained by the equation line, and those two things add up to the total sums of squares. And so we've just calculated the sum of squares residual. It's the amount of variation that is not explained by the equation. So it's this little amount of variation here, 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 and here that is not explained by the regression line that we calculated. But we also need sum squares due to the regression line. And the sum squares due to the regression line is found by basically taking the predicted value minus the mean and squaring that deviation. And so it's basically asking, let's go back to an earlier figure. It's basically asking, to what degree is the predicted value different from the average with a slope of 0 across this whole thing and squaring those deviations. Now, those deviations are going to be somewhat larger because the line lies far from the actual value in some places. Let me go back. I just reduced my thing here and I didn't want to do that. So we've calculated that deviation that gave us our sums of squares residual. Now we want to calculate the sums of squares due to regression. Go back to our Excel file. We can make a new column. Now I need to make my Excel file wider. This new column is going to be y hat minus y bar. Y bar is the mean, y hat is the predicted value. So in this case, for this value here, it would be y hat minus the mean of y, which is here. And since that is going to be the same value every time, we will make that a static cell reference once again, and then we can copy that all the way down. Once again, because these are residuals, these should sum to 0. And once again, it's not exactly 0, but it's very close to 0. And now we can take y hat minus y bar and square that. And square that. And so we're basically just going to take this value and square it. Take all of those things, calculate them, and then add that up. And that is now sums of squares due to regression. So we have 23.5145 essentially. Sums of squares due to regression and sums of squares due to residual should add up to be sum squares total. So this would be what was 6161. Okay, so this would be 6, that would be 10, 3, 11, 24. So I got 24.1306. And what we should see is that if this is sum squares residual, and this is sum squares due to regression, then these two things should add up to sum squares total. Where does sum squares total appear in this spreadsheet?
The sum of squares under the slope of 0.
Yes, that is exactly where it is. Good, good. It appears right here. And we can see that that value is the same as that value. We calculated it 2 different ways, but what it's basically saying, just to get you back in thinking about regression as a method that is a method to describe variation. Well, let's go back. We're done now with this part. No, I have to go back to a figure. Basically, what we have is if we didn't have the x variable, we would think that there's just variation in mass loss that doesn't have to do with anything. This then is the total amount of variation. How far is this value from the mean of mass loss? How far is this value from the mean of mass loss? How far is this value from the mean of mass loss? That's the sums of squares total. That's what we found when we did this, the deviation of y squared. That's the reason that we had this column, is because this is the sums of squares total. Now we're interested in, of all of that variation, how much of that variation is then explained by this line? Well, most of this variation is explained by this line, which is why when we develop how much of the variation is explained by regression, it ends up being most of it, and very little of it is unexplained variation. So how much of that total variation is explained by variation in X? Well, it turns out that it's a lot of it. And we'll actually use these. If we take sum squares due to regression and divide it by sum squares due to that is total, this basically can be used to say how much of the variation in the data set is actually accounted for by the X variable. Well, if sum of squares regression is equal to this, and sum of squares total is equal to that, we can basically divide the amount of variation that is explained by the regression model divided by the total amount of variation, and we see that about 97% of the variation in the y variable is explained by variation in the x variable. This is what a figure called R square is. R square is basically just how much variation in the y variable is explained by variation in the x variable. And in this case, it's most of it. And that should be apparent when you get to a figure like this. Most of the variation in y is explained by variation in x. Very little variation remains unexplained by this regression line. Now, at this point, you are capable of putting everything in here. We have 1 degree of freedom for the regression because we're estimating one thing. We're basically estimating the slope. We have 7 residual degrees of freedom, and we have 8 total degrees of freedom because we have 9 observations total. These are the sums of squares. The mean squared gets calculated by dividing the sums of squares by the degrees of freedom. Mean squared is sum of squares divided by the degrees of freedom. And then the F statistic is the mean squared due to regression divided by mean square residual. Once again, you'll see that's a gigantic F statistic, and as a result, there is a highly significant p-value, basically telling you that your chances of saying that this slope is different from a slope of 0, your chances of making a type 1 error by saying that are virtually non-existent. And so this is actually how we test a regression, is we test the regression with an F test, the same way that we tested our statistical results in an analysis of variance. It's just that the way you generate these sums of squares is different in a regression. Any questions about that? Is it clear how we go about doing this? Okay. The next thing that I want to talk about is actually R square. So these are some outputs from R. And one of the things that you will find when you do the output from R, so here's our R square value is 0.9745. R square value from R is 0.9745. You see that we have the y-intercept estimate, we have the slope estimate. All of these things are the same. We can generate the ANOVA table. The ANOVA table gives us sums of squares and the mean squared. Everything is the same as we did in our hand calculations here. So somewhere down here, we can actually go in and put in an ANOVA table using everything that we know. Our sources are the regression model itself, unexplained, variation, and total. In all of these cases, 1, 7, and 8. Sum of squares due to regression is equal to this. Sum of squares residual is equal to this. Total is going to equal that plus that. Mean squared equals that divided by that. We can copy those two things down. And then the F statistic is equal to that divided by that. And so all the calculations we've done in this figure match up with the calculations that we get through R, 267.2. And then we would have to go and do a calculation with Daniel Soper's website or something to calculate what P is associated with that. but R does that as well. So 7.82 times 10 to the minus 7th is what I ended up having in this. This actually just is a transcription from R. But you don't need R to do all of this, because with simple data sets like this, it's easy enough to calculate the regression on your own. With a gigantic data set, this becomes considerably more complicated, simply because you have more data points to deal with. But in reality, doing it in a worksheet isn't that difficult, because it's just doing a bunch of things to single columns on the left-hand side. So in this way, doing a regression in an Excel file is actually much easier than doing an ANOVA in an Excel file. So let's stop there. Save this spreadsheet in a different file name, because what we're going to do on Monday is we're going to talk some more about regression, assumptions of regression. We're going to talk more about what R square means, but probably towards the end of class on Monday, we'll start getting to some live coding. So on Monday, we'll be back upstairs in 205, and we'll be plunking away in R. So be sure and save a copy of your data file here that is unencumbered by all of this other stuff. So it's just the data without any of these other calculations, because that's what we're going to need on Monday for R. Okay, so save today's work in a different file name. Questions? All right, then I will see you guys on Monday in person in White Science 205. And in the interim, get started on the two-way ANOVA calculations on the two-way ANOVA assignment. And I will see you guys on Monday.